Welcome, everyone, to another episode of Heat Treat Radio. My name is Doug Glenn. I'm your Heat Treat Radio host, also the publisher of Heat Treat Today. It's a pleasure to have everybody. Today, we're going to talk about something really kind of interesting. I've been in the industry quite a few years, and honestly, I had not heard of it. So I think it's going to be something kind of interesting. It is dealing with the treatment of specialty alloy aluminums, and it's called uphill quenching. So we're gonna jump into that today, learn a little bit about that, and talk about it, and get a little education going on here. So to help us navigate these waters, we've got two gentlemen with us, both from Newton Heat Treating. First gentleman is Greg Newton, is the owner of Newton Heat Treating in Industry, California. And Greg's been the president and leader of Newton Heat Treating for at least 25 years. And Greg, I believe, was it your father who started the business?
That's correct. Yeah, I started in 1968, and this was my playground.
This was your playground. This is where you grew up. Okay, that's good. That's good. Joining Greg is John. What's that?
Another son of a heat treater.
Another son of a heat treater. Yeah, as one of the individuals has said, I was born in a heat treat furnace. So probably wasn't quite that bad. But joining him today, on the left side of our screen, is John Avalos with Newton Heat Treating as well. John is a quality engineer and IT manager there at the company, and also in charge of digital transformation. So that's very impressive. And John's here to lend support. And as we were joking around beforehand, he's going to correct Greg. If Greg says anything wrong, he's going to jump right in and make sure everything is accurate. So welcome to both of you. Appreciate it. And before we get started on the questions, I do want to mention and say a word of thanks to Newton Heat Treating, who is in fact sponsoring this episode. So thank you guys for sponsoring it, and you will hear more about them. I'll stop in a little bit and tell a little bit more about Newton Heat Treating, but you can find them on the web at www.newtonheattreating.com. So with that, we'll jump into the conversation. So Greg, let's start with some basics, right? Because as I said, I was not familiar with uphill quenching. So, but I want you to tell, first off, before we even start talking about the process, talk about you a little bit. It's always nice for people to know your qualifications, your experience. How did you get in heat treating and aluminum heat treating and whatnot?
Well, in 1968, my father opened up a aluminum heat treating facility in the city of Industry. And from 13 on, I had a summer job and weekend job. So again, it just was it's part of my blood. And in the early 70s, again, going to the uphill quenching, prior to that, we were the first heat treater to purchase an X-ray diffraction machine, which checks for residual. It's a non-destructive way of checking for residual stresses right beneath the surface of an alloy, aluminum alloy. Different alloys, but we concentrated on aluminum. It's an old analog Rigaku. It's still running. It gives me great data, so why change it out for a $500,000 new machine?
Yeah, right.
So that's how we got started. So this was a pilot project with Northrop Grumman, again, in controlling residual stresses.
Yeah.
And taking glycol out of the laboratory and putting it in production. Now, one thing I didn't like about that project was we gave all the data to Northrop, and then they wrote a spec and gave it to the world. And I didn't feel we got our fair payback for it. Yeah. And so when the M1 tank optics came along, and they knew we had X-ray diffraction on premises. And again, they wanted to take something basically out of the laboratories, which was the lapsed Alcoa patent for thermal mechanical uphill quenching, which does describe the process perfectly. And again, before you can talk about why we use it, or the reason we use it, is because of the residual stresses created during the quench cycle.
Gotcha.
Going from roughly 1,000 degrees down to room temperature rapidly.
Gotcha.
That's up to mechanical properties in aluminum.
So that's good on the. We're going to come back to the process in just a second. I just want to make sure people understood your background. So basically, since you were a kid, you've been in it, and grown up in it, and have specialized in aluminum processing and all the uphill and
luckily I had the last name that I could stick my nose wherever I wanted.
And I'm still doing it. It is nice. It is nice to have that name that you can. Right. Okay. Good. Sure. All right. So you kind of started on this, and I think it's good. 30,000 foot view for someone who has no concept of what even aluminum alloy is. What is uphill quenching? What is it we're talking about doing?
And again, it's not black magic. It's merely the inverse process of the quenching cycle of the aluminum heat, the solution heat treat cycle. Okay. So again, you're going roughly from 1,000 degrees to room temperature, hot to cold. What happens? A part can't cool instantly. So what happens? The outside cools first. It shrinks. You get a compressive shell. By the laws of thermodynamics, I have an equal and opposite action happening in the core of that part. So it develops tensile stresses to hold up that compressive shell. They're in equilibrium when I'm done with the part and I send it back to the machine shop. Then what they're going to do, they're going to remove material from one side. They're going to gun drill it. That's when all hell breaks loose, because at the point of after quench, we have the compressive shell and the tensile stresses in the core. They're in equilibrium. When I remove material array, that compressive shell, that's where aluminum becomes very difficult to machine.
Right, and to solve that problem.
This uphill quench solves this problem.
It solves a problem for all parts, all shapes, all sizes. Okay. So parts that don't lend themselves to flip-flopping, which again never solves a problem. You might machine away some compressive shell, rejig the part, flip it over, remove a little of the compression on the other side. You still have those tensils, and the tensils are the bad guys. That's what's causing a failure in use and things like that, propagating cracks.
And just for most people will know this as listen to this program, but tensile stresses are really the ones pushing out, right? They're pushing out, whereas the compressive strengths are the ones that are pulling in.
And a compressive shell can actually be advantageous for certain types of fatigue like creep.
Yeah.
Where, and we'll get to that on a special one of the projects that we did for Bell Helicopter, which was very
okay. All right, that's good. And then again, a simple question because we're starting with the basics. Uphill quenching is predominantly done on aluminum or only done on aluminum?
Predominantly. We've done a little bit on titanium and had fair results with it. But it was the original Alcoa. Again, Alcoa developed in the late 50s. That's how old this technology is. It's nothing new. Back then, though, engineers used to design things 2.5 times as robust as they needed to be. Just because we didn't know how much residual stresses were inherent in the manufacturing of these parts. But now, trying to lighten up aircraft, cars, everything else, trying to get these parts as light and as thin as possible, comes into play. Yeah. And it's finally come to age.
So you've got the compressive and the tensile stresses, and uphill quenching basically is helping to neutralize or to balance those things so that when you go to machining and you're doing some machining, you're not going to get what you would anticipate with a distortion or something of that sort.
Well, again, we go back to the original patent name that describes the process perfectly. Thermal mechanical uphill quench. We're not stretching it with a hydraulic press to 1.5 to 3% to dislocate the lattices. We're using a thermal gradient. That's our energy.
Gotcha.
That's our machine.
Yeah.
And it's a little harder to wrap your head around, big rolling machine for play. We're going to compress it, right? And get the dislocation that way. Well, this is coming. What put those stresses in was that thermal gradient of the quench, roughly going from 1,000 degrees to room temperature. How can we reverse that? Aluminum, unlike steels, we're blessed being almost annealed soft in an as quenched condition, AQ.
Yeah.
So that is the optimum time, as the original patent tells you. And again, there's so much misconception out there. And again, when you do it in a hardened condition, you've lined up everything against yourself. You've increased the yield strength. You want to do it when the material is as soft as possible. And again, aluminum, you want to either do it immediately after quench within an hour, or retard the natural aging by putting it in a sub-zero freezer.
Gotcha. But basically, the uphill quenching is neutralizing those stresses so there could be further processing without as much fever.
Minus 320 below zero and heat it up with a high velocity steam blast back up past room temperature.
We'll get to that. We'll get to the actual process, but I just wanted to make sure we're understanding why we're doing it. And in this case,
machinability of aluminum, close tolerance parts.
Perfect.
They diamond hone our laser optics to 1/1,000,000 of an inch in aluminum.
Wow. Okay.
That's a tight tolerance.
That's tight tolerance. So and this is a really simple question, but it's always interesting. It's an interesting name, uphill quenching. So basically, I think you've already mentioned it. It's just kind of the inverse of the quench, Right. Coming downhill on the quench, we're going back uphill. Am I wrong, Greg, to look at this as almost like a temper process for a ferrous material, or is it?
Well, no, because all we're doing is we're not changing any of the mechanical properties. All we're doing is a realignment of the lattice parameter of the intercrystalline structure.
Okay. Which sounds.
So again, if you picture that compression pushing in and the tensils pulling out, we're relaxing them back to a neutral state.
But the main point is it doesn't change the temper at all.
Does not change.
Doesn't change. Okay. All right. Very good. All right. Last question, and then we'll jump into a little bit more about what the actual process looks like. Last question before we do that is the uphill quenching. You've mentioned several aerospace companies. Is it, again, predominantly used in aerospace, or is it exclusively used in aerospace, or are there other markets where you use uphill quenching as well?
There's other markets. I mean, any close tolerance parts in aluminum, and the alloys, it's extremely effective on all alloys. 6061, or some sort of 6061 is used in the laser industries or laser optics and things like that. We do a lot with the optical industry.
Right.
Okay. So it's not just aerospace, but a good chunk of it is. It sounds like to me.
Good chunk. Nothing on Mars hasn't come through our hands. I mean, all the gaining and sending antennas, all the optical housings, the wheels even were cold stabilized because they're trying to make them so light, they'd gun drill them and they would collapse.
Do you say nothing on Mars?
Nothing. I mean, all the Mars rovers have all the parts.
Okay. I thought that's what you meant, but I just wanted to make sure I understood that's what you meant.
Actually, our first parts were on Voyager. That we've been looking at this process, and JPL came to us and said, we know you've been doing this, we want you to do your black magic. Dr. Locatel from JPL hand carried these parts over that are still sending data on Voyager that is outside the influence of our sun.
Isn't that incredible?
That is incredible. Incredible. I think it's just so fascinating, the stuff that we do, that this industry does that people don't know about. Okay, so let's jump into it, and this is where you can talk technical. Okay, not that I'll understand it all, but for those people who are interested in it, we'll talk technical for just a second. What goes on in the quenching process? What's the recipe? And if you want to talk about the equipment needed to be used to do it, fire away.
Okay, so again, you want to take these heat treated parts and either within an hour or retard the natural aging. That's key. Again, there are companies and things that do it in a hardened state, and you will get some reduction in stresses, probably more than you will get from any straight thermal stress relief. Right. Where you're just lowering the yield strength and popping some of the lattices, but nowhere near what you'll get in an AQ condition because the materials you've hardened it.
So timeliness is important here. That's probably the first point, right? You want to get it. Okay.
So some of the equipment you'll need a large dewar depending on how big a part you're doing. We have 3,000 gallon tank here on premises and ready to put a 6,000 gallon one in. Then all you're utilizing the LN24 is for its coldness. It's not like other steel heat treaters and stuff where it's in their atmosphere. We're just using
you said it. Let me interrupt you, Greg. You said an acronym, but which you haven't used. LN24.
Liquid nitrogen.
Liquid nitrogen. I assume
right.
yes,
so
but just want to make sure.
Sea level is minus 320.
So you're taking it down to
0. Right. So then you also need some sort of steam boiler or a steam generator. Yeah. We have both on premises. An accumulator, depending on the size parts you're doing, because again, you're using the steam you're trying to reverse the delta T of the quench as fast as possible.
It's a rapid process.
Right.
Yeah, gotcha. That's why steam is very effective at rapidly heating.
Right. Well, and again, as the original report tells you, the difference between you get upwards over 80% reduction in stresses utilizing LN2 and steam versus boiling water, the maximum is around 19%. We've done our own testing and gotten about 20%.
Gotcha. Okay.
So again, significantly higher. And again, doing it in an as-quench condition. The original report tells you get nothing out of doing it in a hardened condition, which is done by many of my competitors.
Yeah.
We will do it here any way you want it. We have boiling water capabilities, but I try to talk you into doing it the preferred way, which is in an as-quench condition, steam, LN2 to steam. That's going to give you your biggest differential in temperature, your delta T. You're trying to match the delta T of the quench, of the heat treat quench in reverse. That's all you're trying to do.
Yeah, it sounds simple. Okay, so you got aluminum as quenched. As soon as possible, you're dipping it into liquid nitrogen to take it down to 320.
Correct.
Roughly, right?
Sure, depending on the thickness of part, it's not a soaking cycle like solution heat treating would be, but you do want to make sure that part is completely at that temperature.
You're right. Okay, so you're taking it down to 320, then immediately taking it out, and you're hitting it with steam for how long, and what's the criteria?
Depends on the size and the shape and the configuration. We have many, many steam fixtures out here that can be slightly modified. We have some customers, it's best to, if you've got a good production run going, to design a fixture specific to that part. Bill Helicopter does it for the rotor grips for the Hueys when they were re-engined.
Are you taking it up then to a set temperature?
Yeah, we want to be above 160 for casting. 180 we prefer for rock products.
Okay, and once it's back up to that temperature, process done?
You're done. Now there are many specs that repeat it, but the original patent tells you that I think this is mostly to make up for lack of fixturing, a part specific fixture. So you can make up with subsequent, and it does come out of the history of the past of when they really didn't understand, before the alcohol patent, there used to be tricyclic stress relieving where they would take it from dry ice into boiling water. And again, one of the advantages of steam, and the reason why you get much better results with steam versus boiling water, is the fact that, one, it's a higher temperature. It blasts away any ice that's forming on that part, on the surface of it.
Yeah, okay, right.
Blast that ice away that's forming, and it's a turbulent flow over that part, so it readily transmits that energy quicker.
Can you also talk about the X-ray diffraction and how you use that to measure how effective the process is?
What we did when we took over this project, and we wanted to prove it out, and we learned a lot of things that perhaps when an engineer patents something, he usually controls everything, and it's not that they're wrong a lot of times, it's that they're 0.000001 right, and in the real world it makes no difference. So you tend to throw those things away because it has no real relevance here on Earth or in space. So we stumbled upon some other things that were advantageous to buy X-ray diffraction. What our standard operation mode was here: first get the part, heat treat it, directly after quench, take a reading. Because we know after a solution heat treating, I have that perfect setup between the compressive shell and the tensils in the core. They're going to be equal or close to it.
Right.
Okay. Now, the thicker the section of the part, the more stress is because it takes longer to cool.
Yes.
So the thicker the part, now when you get into parts with 2-inch cross sections and 1/4-inch webbing, that's when you get a lot of oil canning. All hell breaks loose during the final. We can solve that. And they'll stay. I remember there was a bot part we had for the 767 or 757. It was the door, the pilot's window. And they were failing in service. And the bot had a whole shift Boeing was paying to remachine out of tolerance parts on the shelf, remachine them until they finally were over machined and threw them away.
Yeah.
So we had a hard time, and I did parts for nothing, proved it to them. They adopted it, and then the union fought them, and now that division is closed.
Yeah, and that's crazy.
You have to evolve, or else you go the way of the dinosaurs.
Yeah, you can't fight with science, ultimately. You can't fight with the truth of metallurgy. So that's too bad. So another so I think we've got the basic process. Like you say, it's not that, doesn't sound that complicated. It's a reverse of the quench process, etc.
Attention must be paid to the details, though.
Yes, exactly. Which you don't need to tell us all the details, because then you would be, don't give us all your secrets. That's okay. So let me ask you this, though. I've talked with a couple of other people about this process, and guys, you would probably recognize names. They tell me that the aluminum alloy is somewhat important in the process, depending on what alloy you have. Can you confirm that or deny that? Like if you've got
6061 is a forgiving alloy, and most of the optics we do are some form of that.
Okay.
It's a forgiving alloy in many, many ways. Again, it lends itself to uphill quenching because of its lower yield than the, let's say, 7000 series. Okay. But we've been doing a lot of my work is in 7000 series. Again, it
Okay.
takes a little better steam fixture, perhaps a little more attention to detail. Rough machining becomes into play. How much you rough machine it prior to the final solution heat treating,
Yeah.
and the uphill quenching.
So lots of factors.
Yeah.
Again, we
Well,
like to be
that's
involved not as an after fact. The best successes we've had is when they know it's going to be a problem part. They get us involved in the beginning and we set it up right, and everything goes smoothly.
Yeah.
Instead
And you know
of
what? You had mentioned the X-ray diffraction and the testing of it. Is there anything more we want to say on that?
Yeah, I kind of skipped over it. So I take after the solution heat treat, I'm going to get that perfect ratio of my compressed shell that equals my tensils. So then after the uphill quench, we'll measure again, and then once after aging, because aging can have a slight effect on your stress levels.
Yeah.
So again, that gives me at least a baseline, and I do it for all customers on all first articles. That gives me an internal baseline. I encourage the customers to pay for it, but to a lot of the machinists, it's just an extra cost. But should they ever have a problem in the future, and again, the proof has always been in the pudding. I send it back to them because I can't tell you how many skeptics we've had that call me back and say, "Damn, it really works."
It's working. It's magic.
Yeah, and then some of the failures have come from the successes and thinking, now I can make up the lost time. I'm going to make twice the cuts, twice as deep, twice as fast.
Yeah.
And then you're going to induce stresses by the machine.
You're the hero. You had mentioned something. Again, I want to follow up on this. You had mentioned something that when the engineer initially does the patent, they control everything. They put a lot of stuff in there. It sounds to me like you guys, and correct me if I'm wrong here, maybe I misunderstood what you were trying to say, that in your practical application of this process, you found out which ones of those things are important, and which one of those things can be, that's not that important. Is that a pretty accurate?
We refine the process.
Yeah. So now you don't need to waste time on item X because it really doesn't matter so much. The correlation for success is more tied with item B or whatever.
The boiling water aspect becomes so appealing to my competition because you don't need to use your brain to design steam fixtures and things like that. We've got many steam fixtures over the years, and they're semi-generic. We can change the inserts for cylindrical parts. We found it's very advantageous to steam inside and out simultaneously. And this is a violent. When it says high pressure steam, I have engineers up with their cameras, and I say, no, back away about 30 feet.
Step back from the part. That sounds interesting. It sounds, what you're talking about is the design of the fixtures for the impingement of the steam. Sounds very similar to me to something we've talked to. You may know Joe Powell over at Akron Steel, and some people believe this and some people don't. But he talks about that high intensity quench, again, not uphill quenching, but downhill quenching in this case, where it's really super critical that you quickly and uniformly cool the entire outer shell at the same time. So it sounds like these fixtures you're talking about are somewhat along that line, that they need to be hitting the part at the right place, right time, right volume, and all that good stuff.
Yeah, they represent the configuration of the part as close as we can anyways, so that we get a nice even steam blast.
Yeah.
We'll tend to concentrate steam in thicker areas, and we maybe back off on thinner areas.
Right. Okay. All right. Excellent. Let me take a minute just to do a quick sponsorship spot here, if you guys don't mind, and then we'll come back. I've got probably 3 more questions I want to ask you, and then we'll come right back. So Newton Heat Treating is truly an extension of your company that works to your exact specifications on every type of aluminum alloy and form, from small rivets to large forgings and castings. The company offers its customers fantastic service, on-time delivery, and a competent staff unmatched in the industry, 2 of which we're seeing right here, right? Newton Heat Treating is leading the way in emerging technologies with processes such as cold stabilization and what we're talking about today, uphill quenching, and can provide a real solution for distortion of all aluminum alloys during machining. Their approach to managing residual stresses and its controls over this process, utilizing X-ray diffraction, is unmatched in the aluminum heat treating industry. You can find out more by going to their website, which is www.newtonheattreating.com. So again, just want to thank you guys for sponsoring this.
Thank you for having us.
Thank you, Doug.
Yeah, no, pleasure. So you may have already hit on this, but let me just ask it, point blank. What are the biggest challenges that you face when performing this uphill quenching?
Just overcoming a lot of the misconceptions of when and how to do it.
Yeah.
There's so many different variables out there. And again, I don't want to throw anybody out of doing boiling water or anything like that. We'll do anything you want here. We have capacity for boiling water and steam, but again, I prefer to do it in the correct, the best method possible. Give my customers the best because the price is the same.
Yeah.
So I rather have a happy customer. And I think boiling water sometimes gives it a bad name when it doesn't work. So then they throw out the entire, the baby with the bathwater.
So in the process itself, though, you're talking about the trying to get people to actually do it, but in the process itself, I'm guessing based on what you said that one, fixturing it can be an issue, placement and configuration of the steam is an issue. These are some of the things. I'm guessing part configuration can be challenging, right? The thick to thin cross section. That's what I'm looking for. What are some of those things that kind of, I know you're able to do it, but cause you a little bit of a headache, perhaps, when you see, oh brother, here comes this part.
Yeah, we were doing like Lockheed calls me up and they had a sniper pod for the F-16s and they tried to machine this 1,600-pound hand forging 3 times and we're having trying to go to a one piece monolithic part, and they were having they had one more shot at it, and then they were going to lose the contract. So Don McLeese came to me and he said, "Can you do this?" I go, "Well, you got a rough." They wanted to send me a 1,600-pound hand forging, and I said, "No, you got to rough machine this thing." I go, "How much does the part weigh when you're done?" 168 pounds.
That's crazy.
Jeez, oh man. Wow.
So I said, "You got to rough machine it, then send it to me." Well, so they rough machine it. I get a part 1,200 pounds. So I said, but it was 60-61. So I said, well, we'll give it our best shot. And we did do multiple stabilize on that. I think we stabilized it 3 times, but it worked to a charm. He was worried about just getting this big hand forging back on the machine.
Yeah.
Because it did move a lot during uphill quenching. So we did in between post heat treat, we straightened it, uphill quenched it, straightened it, because each time it'll move less. And you're inducing stresses by the straightening process as well.
Gotcha.
So the third time we uphill quenched it, checked it straight, and it didn't need it. So we shipped it, and they got through this, and we saw another 2 or 3 more. But again, just the challenges of again what they think the process will do and what it's capable of. And I don't think that would have worked in 7,000 series. You really want to get it within 150,000, 100,000s.
Yeah.
Because of the dispersoids they put in the superalloys, make it tougher to uphill quench.
Yeah. A question for you on any other parts that you've processed in the past that were kind of interesting? You kind of go, oh boy, this is an interesting one.
Well, there's one, the rotor grips for the old Hueys. When they re-engined them and doubled the horsepower. Yeah. They went from the 2 blades that you see on the mash, that they could hear from 30, 40 miles away. Pop, 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 pop. Here they come. Well, they switched, they increased the horsepower of the engines, and they went to 4 composite blades. But the rotor grip itself, that they wrapped the carbon fibers around, was a 2014 die forging. And they had machining problems. They would make 1 pass over it, and it would curl up, about 3/4 of an inch. So Gene Williams came down and he spent a week with me. Bell doesn't like anybody else's data. They want to create their own data. And so he was, out there with his camera, measuring and doing everything for a week. And so we got through the machining and laid dead flat. But what they lost in that, when I get rid of the stresses, I get rid of all the stresses, the compressive shell and the tensils. Okay. So they went back to these rotor grips and peened them, glass beaded them. Gave it a nice, even compressed shell without the negative effect of the tensils in the core, and they're getting 8 to 10 times the life expectancy out of these parts now, which makes sense on a fatigue curve. Because you don't know where you're starting on that fatigue curve. And most of them, they go, whoop, you're in that corner and you're done. That's why they stop, they store parts at 50% of their intended life and store them for when they can't get new parts and pray until they get new ones.
Yeah. Very, very interesting. Very interesting. Yeah. I think it's fascinating, the stuff you get in there,
We get the problem part, so it usually gets my foot in the door.
True.
Yeah, yeah. And you did mention earlier it's better for the customer and obviously for you guys if they're developing a part or if they're having an issue, the sooner they talk to you, the better, right? I mean, because yeah, most people really don't take that. They don't think the commercial heat treater or the processor can be that helpful. But with guys like you who have an expertise in the area, it's probably well worth having an early phone call.
Well, no heat treater really loves to see final finished parts. I mean, it's a violent process. I mean,
Yeah.
you'd rather have a little beat on that.
Okay. Let's see here then. Let me wrap a couple more questions. We may have already answered these. Okay, and what type of parts should uphill quenching be performed? Can you give us a quick overview of the types of parts that you've uphill quenched? I think we've already kind of hit on that. But is there anything you'd like to add to that?
Any parts that are moving into machining out of tolerance.
Yeah. Okay. All right. And then, this one you're might have to be very generous on your answer here because I'm going to ask you about competitive processes. So I'm assuming that there are other processes that claim to or perhaps can do something similar to uphill quenching. If not, let me know. But if so, I mean, what are they, and what would be the benefit of uphill quenching over those other processes?
Well, the spec, you've got straight thermal stress relieving, which basically you're just raising the temperature of the part. You have to be careful of losing your temper when doing it. Get a real stress relief out of. You have to go, past, up 600-700 degrees, which is going to throw your temperatures right out in aluminum.
Yeah.
So you tend to use 25 degrees below for longer periods of time. And again, you might lower that tends to break the most highly strained lattices, right?
Yeah.
Because you've lowered that yield strength a little bit and they'll pop. That might be enough to get you through that part in machining. Is it going to move later in service? Probably.
Yeah.
Heating up and cooling down, especially in space. When you have an unstable part in space and it turns towards the sun, gets 200-300 degrees, comes away from space in the vacuum, and now you're thermal cycling. You're actually is a different type of a stress relief.
Yeah.
And it can move those mirrors, and just any slight movement in those mirrors, and you've lost your integrity.
Yeah. Okay.
They can figure out mathematically the coefficient of thermal expansion out in space, but warpage and things like that is.
Yeah. Right. Exactly. So just a business question then to wrap up here. You guys obviously have an expertise in aluminum. What's the radius out of the city of industry to at least to the east? You don't want to go too far to the west. I think you'll be in the creek. But what's the radius you're getting customers from? I mean, how far are people sending you stuff?
I've had Israeli tank mirrors, German tank mirrors.
Oh, okay. There you go.
We've done get parts shipped from the East Coast daily. Hamilton Sunscan, they attribute their position with the success of their uphill quenching on almost all their cylindrical parts. They have a better product than anybody else.
Yeah.
And they told me that they attribute a lot of that to the stability of their aluminum.
Okay. Yeah. Very interesting. All right. So I'm going to wrap up by asking John and you both a question, and it's just going to be just a kind of a summary. John, is there anything that we've missed or that we should hit on, or anything that you thought of over as we're talking that you want to add into the conversation?
Just that we're the leaders in this process. There's a lot of similar processes Greg mentioned with boiling water, and what that does is it forms an ice barrier around the part, and so by doing the steam blasting and uphill quenching, it removes that barrier, and the barrier simply doesn't form.
Ice is a great insulator.
Yeah.
I was going to say, it's
again, if you think of the mechanical process, you basically taken my big hammer and turned it into a little nothing.
Mm-hmm.
Yeah. It almost reminds me with the ice case, let's call it, right? It all reminds me of the vapor barrier when you're trying to quench. Same type. It's an insulator. So okay. Anything else, John? I just wanted to, because I can see things are going on in your head, and I just want to make sure get all the good stuff out of there. So, how about you, Greg? Anything?
No, just that the X-ray diffraction. I mean, having some sort of process control. I mean, here you're spending 10 times a normal heat treat. You're throwing money at a problem, and nobody else has any process control.
Yeah.
And to me, that's like playing Russian roulette with 5 in the chamber, not 1. You know, and your chances of success. And again, we want to know when something goes wrong. Why did it go wrong? You know, without any sort. Can you imagine if we threw out EC and Rockwell out of our heat treatment and say, look, the charts look good. It must be good. We have airplanes falling out of the skies daily. Well, this is you have a very expensive problem, and I just would like to see a little more process control that everybody's doing. NADCAP's trying to tighten that up as we speak.
Yeah. Very, very good. Very, very good. Well, gentlemen, thank you very much. I hope the listeners have enjoyed this as well. I think it's a very interesting, somewhat unique process, and it's good to talk with you two guys about it. So thanks for
challenge any machine shop out there to send me their biggest nightmare in aluminum.
You want to take care of it. Fair enough. There you go. There's an invitation. There's a challenge, guys. He just threw down the gauntlet. Send him your worst stuff, and he'll see if he can fix it. So anyhow, thanks, Greg and John. Thank you so much. I appreciate you guys both being here. We should have up on the screen at this point whatever contact information John and Greg are willing to give. Sometimes people don't give out emails, so if that's not there or phone number's not there, you can always reach them through emailing me. My email will be up on the screen. It's doug@heattreattoday.com. For those of you who are just listening, feel free to email me and say, hey, listen, I want to talk to Greg and John about this uphill quenching. I'll be happy to put you in touch with them. And again, I do want to thank Newton Heat Treating for being the sponsor of this episode. As leaders in the aluminum processing industry, as you can tell from what we've just talked about, you can learn more about them on their website at newtonheattreating.com. If you like what you hear here, please give Heat Treat Radio a 5-star review or a like on Spotify or wherever you watch it. If you don't like it, just ignore don't do anything, because we don't want a bad review. We just only want really good reviews. That'll also, by giving good reviews, by the way, that does help spread the word a little bit more. I know we're an industrial podcast, but honestly, we get pretty good listenership, so it would be helpful. If you have a topic that you would like to hear on another Heat Treat Radio in the future, please, again, email that to me. We'll see if we can find some experts to talk about it, like these two gentlemen did here with uphill quenching. And again, you can just send that to Doug@HeatTreatToday. And then here comes the standard disclaimer. This and every other episode of Heat Treat Radio is the sole property of Heat Treat Today and may not be reproduced in part or in whole without advance written permission from Heat Treat Today. I'm your host, Doug Glenn. Thanks very much for listening. Have a great day.